quality tuition, second best in the Caribbean. Right, so for recording purposes, we're starting alkanoic acids, and on the screen, we have the general formula for an alkanoic acid. Now, an alkanoic acid is real easy to spot. It is have COOH, and that's the most popular form of writing the general formula for an alkanoic acid. If you go through different textbooks, they have slightly different formulas. The C and the H's are just arranged slightly differently, but all of them are trying to say the same exact thing. And you can easily spot an alkanoic acid from the actual diagram. Like if you draw the full structural formula, you all seen in the diagram here, it has a C, a OO, and a H, and one of the oxygens has a double bond. Look at all of them. So from a mile away, it is super easy to spot an alkanoic acid. And all alkanoic acids end with the phrase anoic. Very fitting, right? Because alkanoic acids. Do you all think you all can quickly name the 3 alkanoic acids on the screen? It should be super, super easy. Right, so send the answers. I'll look forward to reading them. The first one only has 1 carbon in it, so he is meth. That means 1 carbon, and you end it with anoic. The next one has 1, 2, 3 carbons, so it's propanonic. Okay? And the last one has 1, 2, 3, 4, 5 carbons, so he is pentanoic. Right, for a question like that, you can only expect to get 1 mark. All right. So let me know when you're finished with everything on the screen, and we will be moving on. So let's see what the next slide holds for us. So now we have to do some reactions of ethanoic acid. It seems like all the different categories of organic chemistry, there's always a section with the different types of reactions. For alkanes, there were different types of reaction, namely for the alkanes, it was the substitution reactions. And we went through a few other reactions, like how alkanes would react with things like oxygen. And for alkenes, the one we did last week, there were so many different types of reactions we had to learn off, mainly addition reactions, and some of the different types of addition reactions were things like hydration, halogenation, and so forth, right? And the same thing went on for alcohols. And I remember telling you guys that for the reactions, for the different groupings of organic chemistry, you just need to learn them off by heart. It's a handful to learn off. So you're gonna every day try to look through them or write it back on a blank piece of paper, okay? So for ethanoic acids, it's not much different. We have to learn of some reactions. There are 2 main categories, anhydrous and aqueous reactions. Anhydrous means without water. So there should be no water involved in the initial stages of the reaction. And aqueous means with water. Right? So I guess you can view it as dry reactions, and the other one as moist or wet reactions, right? Those are not the chemical terms, obviously. That is just how I want you to imagine it. Okay? So take down the 2 different categories of reactions we're going to be exploring today, right? I'm sure you all probably did already. All right. So just take a 10 seconds and we will move on. All right, so let's move on there. That's about 10 seconds. But before we go on, right, you'll notice that the name of this organic compound is alkanoic acids. Key word there is the word acid. So an alkanoic acid is it's a type of acid, just like hydrochloric acid, sulfuric acid. But quick question, if they ask you this in the exam, is alkanoic acid, is it a weak acid or a strong acid? What's your answer? Alkanoic acids, weak or strong? Right. The answer is alkanoic acids. I said it like that on purpose, right? Is actually a very weak acid. Despite its very fancy name, alkanoic acids, the name doesn't do it justice. It's a weak acid. So you all are probably wondering, well, what's the difference between a strong acid and a weak acid? Well, in chemical terms, it has to do with the dissociation of the ions. For example, in a strong acid like hydrochloric acid, this is a strong acid. When you put hydrochloric acid or HCl in water, let's just call it water, right? All of the hydrogens and chlorines will separate, they dissociate. So you get hydrogen ions and chlorine ions. So look at it. Now, obviously, there will be millions of molecules inside. I only had time to draw 3. But in a weak acid, when you put it in water, not all of them will dissociate. You notice in this one here, 2 of them remain together. The hydrogen remain bonded with the rest of the ethanoic acid. Or some of them will dissociate, meaning some of them, the hydrogen, will separate from the rest of the compound. And that's the difference between a strong acid and a weak acid. In a strong acid, all of the ions dissociate. But in weak acids, not all of them associate. What we want in a strong acid is as much hydrogens to be as free as possible. In the weak acid, only one of them in this particular diagram, one of the hydrogens was able to gain his freedom. The rest of them remain bonded to the rest of the structure. All right. So we already did this when we did acids. So you don't have to take this down. You all probably already knew this, right? So I'm going to move on from this point. Right, so here we have 2 examples of anhydrous reactions. Only one of them we're going to be discussing right now. The first one is that ethanoic acid, right? It burns in air, right? This also burns, right? I put burning by mistake, sorry about that. Ethanoic acid burns in air or oxygen to produce 3 things: carbon dioxide, water, and heat, which means this is an exothermic reaction. And I have the symbol for exothermic on the board here. This here is the formula for ethanoic acid. And I know it from looking at it because it has how much carbons? 1, 2 carbons. And we see the COOH. So we know it's what? An alkanoic acid, but the 2 C's give it away, and we know the name, it's ethanoic acid. The second type of reaction, which it seems I've been breaking since last week from explaining, is something called esters. Whenever we mix ethanoic acid with an alcohol, it produces 2 things: esters and water. Now, remember, anhydrous, I know I said anhydrous are dry reactions, but that's at the beginning of the reaction. At the beginning of the reaction, there was no liquid, right? No water or whatnot. I mean, we got water out of the reaction, but we didn't need the water at the beginning of the reaction, okay? So take down everything on the screen. And of course, eventually I'm gonna have to show you that stuff with the esters. Like I'm gonna show you an official equation where we take ethanoic acid, mix it with alcohol, and you see this complex thing called an ester. Right? But be patient, I'll reach there for sure. But this one here, the state symbol for the acid it's liquid, and that's an L there. I know it's hard to see, but that is an L. Now, liquid is different from aqueous. Remember that. Aqueous means it's dissolved in water. That ethanoic acid has no water in it. It's possible to be a liquid without water. I know some Form 5s and some Form 4s had trouble imagining that. People have the habit of imagining that anything that is liquid must have some water in it. But ethanoic acid, that could have zero water in it. Hence the L. So let's move on to the next screen here. Here are some other reactions, but this is the aqueous reactions, the ones that involve water. And if you look at all of them, right, I'm not going to read through all of them because I think you all can more than, reason out all of these. All of them have an AQ on them, meaning that it's dissolved in water. So it has something to do with water. Also, you'll notice in all of them, the hydrogen is getting kicked out and being replaced by the metals. If you all notice that, because all of these metals are more reactive than hydrogen. So if you look at the metal reactivity series, it will replace it in a reaction. All right. Also, the charge on CH3COO, the H part is positive, and this entire part has a 1 negative charge. So because magnesium is a group 2 metal, when it replaces the hydrogen, remember the hydrogen has a charge of positive 1. For CH3COO to balance out magnesium, you need 2 of it. If you look at it, there's 2 of it to balance out the positive 2 magnesium. All right, so take down everything on the screen. And of course, please practice writing back all of these equations in your spare time. Okay. Right. So before we move any further, right, before we move on to esters, I want to talk about this word, the homologous series. That seems like a very big word, right? But let me explain what a homologous series is. You see how we did alkanes, we did alkenes, we did alcohols, what we just did, alkanoic acids. Each one of them is called a homologous series. And you will notice something about the homologous series, like everybody in alkenes, you notice all the alkenes have a kind of look, like all of them have single bonds in them. And how alkenes, you can spot that from a mile away because it have like a double bond. And alcohols, real easy to spot, it have an OH at the end. And which one we just did? Alkanoic acids, that has a COOH. But everybody in alcohols behave a certain way. All the alkanoic acids, they're not exact, like metanoic acid is different from ethanoic acid. And of course, that's different from pentanoic acid. But if you look at all of them in one group, they have something similar amongst them, right? For example, alkenes. All alkenes, most of them are colorless. But as you go down the alkene structure, like you start from methane, and go to ethane, and then propane, you will notice that the boiling points or melting points will gradually increase. And this here is a summary of all the things that are similar to all of the different categories we did so far. All right, so give it a read, take it down, let me know when you are finished. Finally,